Hello everyone, welcome to my calculus lecture. In this lecture, we study maximum and minimum. So we begin with the following definitions. A function f has an absolute maximum at c if f of c is greater than or equal to f of x for all x in the domain of f. So, simply speaking, absolute maximum is really like the largest possible the value of f of x in the domain. Okay, uh, and a function f has an absolute minimum at a point c if f of c is less than or equal to f of x for all x in the domain of f. In other words, the f of c is the smallest possible value in the whole domain of the function f. On the other hand, there is another notion of the maximum and minimum values. So we call them local maximum and also local minimum. So what is a local maximum? A function f has a local maximum, or another name is relative maximum at c if f of c is greater than or equal to f of x in some neighborhood of c. So, in mathematics, when we say neighborhood, neighborhood means an open interval, okay, an open interval. So, in other words, the f has a local maximum at a point C if f of x is greater than or equal to f of x in some, the open interval containing C. Okay, that's what it means. Similarly, a function f has a local minimum or relative minimum at c if f of c is less than or equal to f of x in some neighborhood, some open neighborhood of c, in other words, in some open interval which contains c. So as you can clearly see from these definitions, okay, a local maximum may not be necessarily become an absolute maximum. The same is true for local minimum as well. A local minimum may not be necessarily a local absolute minimum. Okay, so a simple analogy is there's person, okay, there's person who is, let's say the richest person in the state of Alabama, okay, but he may not necessarily be the, richest person like in the South even, okay, right? So that's the thing. So, he is a local maximum. Okay, so maybe in the state of Alabama, he may be the richest person, but in the say whole like southern region of United States, he may not be the richest person. Okay, right. So that's kind of like the simple example. Okay, so let us take a look at the following example. So what we are looking at here is the graph of f of x, which is 3 times x to the power 4 minus 16x cubed plus 18x squared on the interval, closed interval, negative 1 to 4. Okay, negative 1 to 4. So from this picture, we can see that, right? There's like a local minimum and local maximum, okay, and also local minimum here as well, right? So It may not be quite clear, like from this picture, right? But actually, there's a local minimum. Right. So the earlier like figure one, right? Figure one shows a graph of this function here, right? Like I mentioned, so it has a local maximum at x equals one. Okay, at x equals one, it has a local maximum at x equals one, and also a local minimum at x equals three, right? X equals three. You see a local minimum there. But the local minimum in this case, the f over 3, which is negative 27, is also absolute minimum, right? So let me go back to the picture. As you can see here, that's actually the f over 3, which is negative 27, is the smallest possible value of f of x in this domain, right? From negative 1 to 4, negative 1 to 4. And also, the f has an absolute maximum, but in this case, there is absolute maximum at the boundary point negative 1. Okay, let me go here, right? So that's f of negative 1 is the largest possible value of f of x, okay, which is 37, okay, which is evaluated to be 37. But it can't be a local maximum though, right? Why is that? Let me go back. Okay, so f of negative one. This is the absolute maximum, but it cannot be a local maximum. The reason is simple because negative one is a boundary point. So no matter how small neighborhood open set, the center that negative one you take, there's portion, right? There's portion, that so you know uh, precisely like those values of x that are less than negative one, they are not part of this domain. Okay, they are not part of this domain. So you can't say that like this is uh, I mean greater or or like the less than like the functional value, because I mean there's no functional value for the those x values, okay, those x values that are less than negative one, because they are not part of the domain. So that's why the at the boundary point cannot be at the boundary point. You cannot have a local maximum or local minimum, right? But what we can see here is that absolute maximum or absolute minimum are not also necessarily be local maximum or local minimum, right? They, you know, they could be just the value of your function at the boundary point. Okay, right. So that's the important thing you have to keep in mind. We are going to come back to that aspect later on. And also here, like we see another like a local minimum, right? At x equals 0. All right. So hopefully, right, by now you can clearly see the distinction between local maximum, local minimum, local absolute maximum, and absolute minimum. Okay, so here's an important theorem. So before we talk about it, all right, so here's a question. Uh, Even like assuming that the function is continuous, okay, continuous function, does it always have an absolute maximum or an absolute minimum, right? It's not necessarily true. Okay, it's not necessarily true that even a continuous function can, have it, always have like always has like a local maximum, or I mean absolute maximum or absolute minimum. Let me show you an example for that. Okay, so for instance, let us consider the function here. Y equals x. That's a straight line, right? On the entire real line as its domain. Okay, so you know the graph, right? It's supposed to be a straight line, so let's just pretend that this is straight line. Okay, this is, yeah. I can't really make it straight, but so that's graph of the y equals x, right? So it keeps it standing, as x goes to infinity, and it keeps it standing, uh, this way also when x goes to negative infinity. So as you can clearly see, right? The value of uh, f of x, y, that goes from negative infinity to infinity. All right. So in this case, no, neither, neither absolute maximum nor absolute minimum, right? So that's a simple example which shows you that a function can have neither, okay, neither absolute maximum nor absolute minimum. So another example, uh, we consider like y equals x squared on the half open or half closed interval. So 0 closed, 1 open, right, on this interval here. In this case, right, so let me draw the graph. So graph goes like that. Oh, no, this is not it. So it goes like that. And so here, this is 0, right, origin. So, the 0 is included, okay, 0 is included, but at 1, it's not. So I'm going to put a circle there. Right, so that's the x equals 1. Okay, right. So as you can see, clearly see from this picture, right, it has a local, well, actually, absolute minimum, uh, f of 0 equals 0, right? So that's absolute minimum, but no absolute maximum. Okay, no absolute maximum here. At x equals 1, by the way, this is not, there is no maximum here because, x equals 1 is not included. Okay, so again, this is another example, all right? Not so necessarily, uh, even, even for a continuous function, right? Not necessarily there is, there can be both like absolute maximum, uh, an absolute minimum. All right. But what this theorem, which is called the max-min theorem, it is due to the French mathematician Fermat. What it says is the following: if f of x, if f is continuous on a closed interval, that's very important. Not just continuous, but if f is continuous on a closed interval a b, then it is guaranteed that f has an absolute maximum and an absolute minimum on that interval, closed interval a b. Okay, that's very important, right? And also, there's another theorem, okay, due to the same mathematician Fermat. What it says is if f has a local maximum or a local minimum at C, and if f prime of C exists, then f prime of C equals 0. However, the converse of this theorem is not necessarily true. Okay, the converse of this theorem may not be true. Okay, so actually this statement here can be easily understood, if you take a look at a picture here. Okay, so yeah, I went back to, the earlier example, right? So as you can see, at x equals 0, x equals 1, and then also x equals 3, right? We have a local, so local minimum here at x equals 0, and local maximum values at x equals 1, and also x equals, oh, yeah, that's a local maximum, and another local minimum at x equals 3, right? So these are, in fact, this is polynomial, right? This is polynomial, so differentiable. So f prime of x exists at those values, right? Okay. And so what is like a derivative? Derivative is a slope of a tangent line. So if you draw a tangent line at each of those points, so at x equals 0, x equals 1, and x equals 3, those tangent lines is going to be horizontal lines. If you draw a tangent line there, they are going to be horizontal line. In other words, the f prime of x is going to be 0 at those, local, at those points where f has a local maximum or local minimum. So from a picture, it can be easily understood. Okay, so that's what this, the Fermat's theorem says. If f has a local maximum or a local minimum at C, and if f prime of C exists, then f prime of C equals 0. By the way, the having the function having like a local maximum or local minimum does not necessarily mean that the derivative exists. Okay, I'll give you a simple example. Yeah, what I intended to draw is the graph of it. The y equals the absolute value of x. Okay, absolute value of x. Right. So here at x equals 0, you know, the we have talked about this in a while back, right? So this function here, the absolute value of x is not differentiable while continuous. It is not differentiable at x equals 0. Okay, So in fact, we have this sharp corner, right? So when you have it from the if the graph has like a sharp corner, at that point you don't have derivative there. Okay, so it's not differentiable. Anyway, so we know that it is not differentiable. However, x equals 0 is a local minimum in this case. Okay, local minimum because the you see, f of 0, right? F of x being like a square root of, I mean, the absolute value of x, right? So f of 0 equals 0 is actually smallest possible value in some neighborhood, right? In some neighborhood containing 0. So it is actually local minimum by definition. However, derivative does not exist at that point. Okay, so here's a definition. A critical point, okay, a critical point of a function f of x is a number c in the domain of f such that f prime of c equals 0 or f prime of c does not exist. Okay, right, that's important. F prime of c equals 0 or f prime of c does not exist. Okay, so in the earlier example here, and x equals 0 in this case, what? The derivative does not exist. So in this case, x equals 0 is a critical point. By the way, why the name critical point? Okay, the word critical it is appeared in many different places. Say, in physics or chemistry, like, you hear about like, say, critical temperature. So, the critical temperature is a temperature at which, like, the state of matter changes, like, so, water becomes like water vapor, gas, right? Or like, the other way around, like, the water vapor becomes like water, or like water becomes like ice, and so on and so forth, right. So that's a critical temperature. Okay, and also like in medicine also, like I say, you often hear like there's a the patient in the ICU, and doctors say like the patient is in a critical condition. So what does that mean? The patient's condition is so bad that he's at the moment of like the life or death, right? So critical means like the state, right? The certain state changes at that point. At that point. So in our case, what do we mean by a critical point? So I actually went back to our earlier example again. So x equals 0, the function has a local minimum, right? You can see the function is decreasing, right? Decreasing on the left side of 0. And then once it hits the 0, the critical point, this is critical point because f prime is 0. But then, the function started increasing. So it changes the state of function, right? From decreasing to increasing at x equals 0. And same thing happens, a similar thing happens at the critical point x equals 1. The function is increasing and then changes to, its state changes to decreasing. At x equals 3, right? So, on the left side of x equals 3, the graph, the function is decreasing. And then at x equals 3, right? Once it hits, the x equals 3, it started increasing again, right? So that's why, those points, right, critical points, I mean, they are actually called, critical points. Okay, so here's it. important thing, right? Unimportant thing. So we know about like absolute maximum or minimum, but the question is like, how do we find them? So this is a practically important question, right? How do we find them actually? So actually, I wrote down a recipe, okay, a recipe for finding absolute maximum and absolute minimum. So it's actually fairly simple. You just need to follow this recipe, right, and it'll get you the absolute minimum, maximum, and absolute minimum values of a function, right? So let f be a, oh, there's typo. I gotta fix this. Let f be a continuous function on a closed interval ab. Okay, closed interval ab. So by Fermat's max-min theorem, we know that f is guaranteed to have the absolute maximum and absolute minimum, right? So here are the steps. First step, find all critical points of f in the open interval AB. Okay, find all critical points. And then step two, evaluate f at each critical point in step one. All right. And then step three, find f of a and f of b. These are actually a and b are the boundary points, right? So evaluate your function at the boundary point. So what are we doing here? As you might have noticed, I was explaining that earlier, right? With the our first example, okay? you know, absolute maximum or absolute minimum. So the candidate uh, of the absolute maximum and absolute minimum can be always found among those local maximum and local minimum values, or at the boundary point. They can be found at the boundary point. So basically, what I'm doing here from step one through step three is putting all those candidates. So the possible candidates for the absolute maximum and absolute minimum. But then, how do we single out the absolute maximum and also absolute minimum, right? Easy. That's my last step, step four. Put all those values together and then compare them. We have only finitely many of those, okay? So compare them and pick the largest value, that's going to be your absolute maximum, and pick the smallest value, right? Least value, that is going to be the absolute minimum. It's simple as that, right? So finding absolute maximum and absolute minimum is not hard at all, okay? So let us take a look at an example. Find the absolute maximum and the absolute minimum values of the following function: x cubed minus 3 times x squared plus 1 on this closed interval -1/2 to 4. Okay. So to work on it, let me get to my notepad. Oh, you know what? I just remembered, before I actually work on that example, there's something I wanted to talk about, but then yeah, I forgot. So yeah, this one here, right? Yeah, the Fermat's theorem. If f has a local maximum or a local minimum at C, and if f prime of C exists, then f prime of C has to be 0. Okay, but the converse of this theorem is not necessarily true. And then I didn't go any further, right? So I forgot. Okay, sorry about that. So that means that there is an example, right? There is an example, right? That the counters the converse of this theorem. In other words, so f prime of c equals 0, but the f has uh, no local maximum, nor f doesn't have f has neither local maximum nor local minimum at x equals c. Okay, right. So here's an example. Let me talk about that first, and then I'll get back to the example. Okay, so let's consider the following function: y equals y equals x cubed. Okay, y equals x cubed. So let me draw this graph. This is a well-known function, right? And oh no, the graph goes like that. Okay, so that's the graph of y equals x cubed. So let's call it f of x, right? F of x. So f prime of x equals 3x squared. Okay, so the if you set this equal to 0, we have x equals 0, right? X equals 0. And but the thing here is that f of x equals x cubed has neither a local max nor a local minimum at 0. Why is that? So this is x equals 0, right? This is x equals 0. You know, so here f of 0 equals 0, f of 0 equals 0 is always less than or equal to, the any f of x, right? For x on the right side of 0. But then, f of 0 equals 0 is always greater than or equal to any x which are, on the left side of 0. All right. So because of that, no matter how small neighborhood you take, centered at 0, okay, it always happens. It always happens. So which means that, f of 0 equals 0 is neither a local maximum nor a local minimum. So this kind of point here, f of 0 equals 0 is called a saddle point. Okay, a saddle point. Saddle, a saddle as in like what, a horse saddle. Okay, right. Okay, so now we are gonna get back to the example we were going to talk about. Okay, so example. Okay, so our function here is f of x equals x cubed minus 3x squared plus 1, and its domain is negative 1, the closed interval, right, negative 1 to 4. Okay, right. So we are going to follow the step. So step 1, okay, what is the step 1? Right, step 1 is find all critical points of f, right? In the open interval, so find all critical points. So we are going to take the derivative, right? So f prime of x. This is differentiable function. So the finding critical point is solving this equation, f prime of x equals 0, right? So in other words, in this case, f prime is 3x squared minus 6x, okay? Now, 3x is a common factor, so I'm going to factor it out. That leaves x minus 2. So set that equal to 0, and so this equation has two solutions, right? X equals 0 or x equals 2. So these are the critical points, okay? These are the critical points. Step 2 is evaluate these values, right? I mean, evaluate your function at these values. So f of 0, that's obviously 1, right? And f of 2, that's going to be negative 3, okay? Right. Step 3, we are going to also calculate, the value of f at the boundary, right? So the boundary points are negative 1/2 and 4. So f of negative 1/2, that's 1 over 8. That's 1 over 8. And f of 4 at the right end point, we have f of 4 equals 17. And then what is the last step? Step 4, we are going to compare these values, right? So we have f of 0 equals 1. So these are all possible candidates for the absolute maximum and absolute minimum. Okay, so put them all together and we are going to compare. Then we pick the smallest one. In this case, smallest one is this guy. F of 2 equals negative 3. That will be the absolute minimum, right? The absolute minimum. And the largest possible value is obviously this guy here. F of 4 equals 17. That's going to be the absolute maximum. As easy as that, right? Okay, so that will be the end of my lecture on maximum and minimum. More details of my discussion in this lecture can be found in my lecture note at the following address. And as usual, for your convenience, I made, hyperlink to this address. So all you have to do is just click your mouse button on it, and it'll take you there. Or if you want to visit my main blogger site, click it on this word blogger, which is also hyperlinked. Okay, so there you will find the many other also lectures, my lecture notes. Okay, so thank you folks for watching and listening to my lecture here. Bye bye.